Okay, yeah, thank you all for being here. I will give a talk about single-source unsplittable flows, and I will focus on its application in machine scheduling. This is based on joint work with Martin Skutella and based on work by Lars Rohwedder. Okay, so let's start with single-source unsplittable flows. So this problem has been introduced by Kleinberg in '96. We are given a directed graph D and a vertex set V, an arc set A. And now we are given a single source S and K commodities. And each commodity consists of a terminal Ti and a positive demand Di. Now the task is to route each demand unsplittably. This means that for each terminal Ti we choose a single path from S to Ti, and the whole demand is routed on this. So we'll have a look at this example. So as you can see here, the sources on the left-hand side, we have three commodities. So one terminal is here with demand value 4. Then we have one here with demand value 1, and one here. And as you can see, we've chosen, this is an orange path from S to this node here. The purple one is routed along this path, and the green one is routed along this path. Now, if we allow the demands to be split up, this is just a simple network flow problem. And if we are given R capacities, this problem is NP-hard. Probably can use this one as well. Now, we're not focusing on the general unsplittable flow problem today, but on this version where we want to turn an arbitrary flow in a graph into an unsplittable one. So the goal is now that we are given this arbitrary, like simple network flow X, and we want to find an unsplittable flow Y such that each flow value on the arcs does not deviate by too much. So YA is more or less XA on all arcs. So the first question is what can we expect for those unsplittable flows to attain? And as you can see on the left-hand side, this gives us a certain upper bound. So we have a source here, and we have one unit of demand here that is split up along all possible paths. So we have a flow value of 1/k on all arcs. And now if we want to find an unsplittable flow, of course we have to choose like one of those, and all the others are 0. So we are arbitrarily close to an upper bound of XA plus the maximum demand that is rooted in our graph. On the other hand, if we have a look at lower bounds for those flow values YA, we have K demands here of 1 unit. The flow X, like on all solid arcs, we have a flow value of K over K plus 1. So most of the flow is like going directly from S to the terminals. And then we have like K over K plus 1 here, and then it is split up and is like coming from the other side with a flow value of 1 over K plus 1. Now, if we choose an unsplittable flow here, it means that on one of those solid arcs we have flow value 0. So we are very close to a lower bound for those flow values of XA minus Dmax. So what we are conjecturing, this is joint work with Martin, is that for a given flow X, there exists an unsplittable flow Y such that the flow value on all arcs satisfy a lower bound of XA minus Dmax and an upper bound of XA plus Dmax. And those examples show you where like those upper and lower bounds are coming from. Then, so this is what the best that we could expect, but this is not what we've seen, what we've shown. And this is actually related to Guman's conjecture from 2000. Michel was focusing on upper bounds here and was working with cost in the arc in the graph, which is a slightly different problem, but it's closely related and inspired by this conjecture. Okay, is there? I'll just have a look at the. Oh, okay, yeah. Hopefully. Okay, let me just continue, I guess. Yeah, seems to be a problem, yeah. Okay, so let's have a look at known results for those arcwise upper and lower bounds. First of all, in the paper of Dinets, Garg, and Gumans from 1999, they oh, okay, good. They already showed that for a given flow X, there exists an unsplittable flow Y, such that those upper bounds we're interested in are satisfied. So this proof gives rise to an efficient algorithm, but is unfortunately, well, they're probably not adaptable for handling those arcwise lower bounds we're also interested in. So we had a look at those lower bounds, and we could show that for a given flow, there exists an unsplittable flow Y, such that YA is at least XA minus Dmax. This is actually what we want to have. Unfortunately, this is just a proof of existence, but it works with very simple augmentation steps. So the tool we're using is very, very simple in structure, but only gives a proof of existence. So it's not algorithmic yet. This is work in progress. And now we're looking at arcwise upper and lower bounds simultaneously. So here, if we only allow demands to be integer multiples of each other, then for a given flow Y, we can actually prove the conjecture. So there exists an unsplittable flow Y such that YA always lies between XA minus Dmax and XA plus Dmax for all arcs. For arbitrary demands, as you can see, we have a slightly weaker bounds. We have a factor of 1/2 here and a factor of 2 here. So the proof of this special case is via a rounding procedure that has already been described or inspired by those two papers, Koleopoulos and Stein from 2002 and Skutella from 2002. And we're doing for the arbitrary cases that we round down to the special case. So this is why we get those factors, and it's actually quite difficult to overcome those two factors. This does not seem to be trivial with this approach of proving it. Okay, so this was the introduction for the unsplittable flows, and now we're actually coming to the part of applying it to machine scheduling. So for those who are not convinced by unsplittable flows, this is for you. So how are unsplittable flows and scheduling related? And we are looking at this problem called maximum flow time problem. We are given a set of n jobs, and each job has a release time, so release date Rj and a processing time Pj. And we have a set of m machines, and each job can only be processed on a restricted number of machines. So for each job, we have the set mj that is given, and those are the jobs that can be used for this job. And the task now is to process each job preemptively. So once we get it started, it has to finish. And we want the maximum flow time to be minimized. It means that's the time a job spends in the system. So the completion time minus the release date. A quite classical problem in machine scheduling. It is NP-hard, and the best known approximation factor is actually of log n, which is due to Bansal and Kulkarni from 2015. So what we want to do now is we assume that this conjecture is true, and not only in this kind of existence way, but we actually want to assume that such a flow can be found in an efficient manner, say algorithmically. And we're going to show that if we assume this conjecture to be true in this efficient manner, we would actually get a constant factor approximation for the maximum flow time problem. So what I'm going to present here now is work by Lars Rohwedder from IPFL. Some parts of it, so for example, this IP and LP relaxation has already been used in this paper from Bansal and Kulkarni for the O log n approximation. So just to make it clear here. So we start with the maximum flow time problem, and we reduce it to this unsplittable flow problem. This will be the first time we're working with the solution of an LP relaxation, turn it into a fractional flow. I will show you what kind of graph we're having and how to translate it to a fractional flow. This fractional flow gets actually turned into an unsplittable flow via this conjecture we're assuming. And then the unsplittable flow as a second step can be translated to a solution of the IP. And actually, we're going to see that the analysis turns out to give a constant factor approximation. Are there any questions so far for what we're going to do? Okay. So let's come to this IP for the maximum flow time problem. This has already been used by Bansal and Kulkarni in their paper. So we want to minimize this maximum flow time, which I denote by op. So this is actually the maximum flow time of an optimal schedule of the job. And our variables here, yij, are actually one whenever a job is assigned to a machine. So it has to be 0 whenever I is not in the set mj, because the job, of course, can only be processed on those machines that are in mj, and is 0 or 1 independently on if we're using it or not. The most interesting constraint is actually this one here. It says that whenever a job is released during an interval t prime, then it must be completed by the time t prime plus the time of the optimal schedule. So it has to be completed by time t prime plus opt. And so the total size of such jobs that are actually assigned to this machine can be at most t prime minus t plus opt. And now we're restricting ourselves to t prime being within the set of release states, as those are actually the tightest bounds. And you will see in the end, this constraint is actually quite important for the analysis and in the end. So far, so good. Okay, so we'll come to the LP relaxation. So now I denote variables by xij. In fact, it's related to the fractional flow and the unsplittable flow. This is why I'm using the variables as I do here. And xij is now the amount of time a job j spends on a machine I. Again, we're assuming that it's 0 whenever I is not an mj. It can lie between 0 and 1. And again, we cannot assign too many flows or too many parts of those jobs to the machine within a certain interval. So I hope this relaxation is clear as well. So from this LP relaxation, we get an instant xiy, which then corresponds to the optimal value of this relaxed version. And of course, as we're minimizing, we have a relaxation, so this value opt bar is at most the optimal value, or the value of the optimal schedule. Okay, so the first step has already been taken. We have now the solution of an LP relaxation that we have to translate to a fractional flow. So the next step is now the stage 1, so reducing the maximum flow time problem to an unsplittable flow problem. So what we want to show is now that we're given this instance from the scheduling. So we have jobs j with those release states rj and the processing times. We have the machines, and for each job mj. And now we want to construct a digraph. We're now in the setting of those unsplittable flows. So we have a digraph D with a node set, and this node set first of all contains a single source. Then for each job, we have one sync node tj with a certain demand, and this demand is in fact the processing time of each job. And now for each machine, we have one copies of nodes that are actually corresponding to the release times. So I denote them by R1i and to Rni. We'll have a quick example afterwards to see how it works. For the arg sets, we have for each machine the args s to the first node of this copy, and then going from one to another one. And for each job, we add those args rji to tj, so to the terminals, whenever I is in the set mj. Okay, on the right-hand side, it's pretty small. You have the explanation again. So we'll have a quick look at this example where we have n jobs with release dates, RJ, processing times, and 3 machines, M1, M2, M3. So for the first 2 jobs, we can use the first 2 machines. The third job can actually be processed on all machines, and job 4 and 5 can be processed on machine M2 and M3. So the construction, first of all, gives us this node set. So a single source on the left-hand side. Then we have for each job a sync node Tj with this demand Pj, and for each machine a copy of nodes R1 to Rn. And then let's come to the arc set. Those are all directed arcs from left-hand side to right-hand side. I just skipped it in order to keep it clean. So for each machine, first of all, we have an arc from S to the first node of each copy, and then it simply goes through all of those nodes. And the last step is now to add the last set of nodes. So for each job, whenever a machine is an MJ, we add this arc RJ to TJ. And of course, those are also directed. So we're done with the construction. We have a unique STJ path whenever a machine is in this machine set MJ. So for each job J and each machine I, so for all TIJs that could be possibly positive, there is a unique path. So this translation from our solution of the LP relaxation can be actually translated quite forward. So the amount Xij, which is actually the amount a job J spends on a machine, is actually routed along this unique STJ path. Any questions so far? Okay, so if we have a look at the flow value on those arcs, especially those who are lying within this machine, we have that XA is actually the sum of all L at least J of XIL. So whenever we have an index that is at least J, it has to be routed along this arc. Because the path would actually, if we would go from M1 to T3, the flow value X, what is it then, 1, 3, would exit at this moment here. So it would use the arcs that are coming before that. Okay, I hope you're still with me. So we had this first step, we reduced this first stage, we reduced the maximum flow time problem to the unsplittable flow problem, and turned the solution of the LP relaxation into a fractional flow X. Now we're actually working just in our graph. We're assuming that our conjecture is true. So this fractional flow can be turned in an unsplittable flow Y, such that those lower and upper bounds we've been looking at in the beginning are satisfied on all arcs. And now we have to go back to the IP. So the translation is actually quite simple. We have an unsplittable flow now in this graph. So a job J can actually be assigned to a machine MI whenever the demand is routed along this copy of nodes corresponding to the machine MI. So for the first node, for example, if I have chosen this path here for the unsplittable flow, of course job 1 is assigned to machine M1. And also, as you've seen before, our conjecture would imply that YA is at least XA minus Dmax, or in fact, in this time, it's the processing time, so Pmax, and at most XA plus Pmax. Okay, so this translation is actually quite straightforward, but we have to have a look at the analysis now of the approximation factor. So let's first recall that if we have a look at one of those arcs lying within a copy of nodes corresponding to a certain machine, that XA is the sum of all indices L at least J XIL. So this is the sum of the fractions we've had in the beginning. The same, of course, is true for YIL, because they're also using the same arcs and the same paths. So if we look now at all jobs summed up for the release time RL being within RJ and RK, it is actually the difference of the flow value on the arc RJ minus 1 RJ within this copy of nodes, and RK plus 1. I hope that this is clear. This comes just from the construction we've been using for our graph. And now, as a second step, we can use our conjecture, so the upper and lower bounds coming from it. So this flow value here is at most XA plus P max, and the other one is at least XA minus P max. So we can already see that this value here is bounded by the flow by the sum over all RL lying between RJ and RK of those fractions we've been assigning to machine I. And we have, of course, this additional factor of 2 P max here. Now, Xij was a solution of this LP relaxation. It corresponded to the optimum in our relaxation. So we know by this first constraint I was mentioning in the beginning that this is at most RK minus RJ plus opt bar. And Pmax is the processing time, the maximum processing time, so it also is bounded by the optimal value. And the optimal value of the relaxation was also bounded by the optimal value, which means that now we know that this one here, this sum, is at most RK minus RJ plus 3 opt. And if you recall the constraints we've been having, this actually means that all the total size of flows that have been assigned to a machine within this interval T2, T prime, all this total size is done by RK minus RJ plus 3 times the optimal value. So we have a 3 approximation here. I hope you're still following. Okay, so what did we do? We started with this solution of the LP relaxation. So we had this instance Xij that corresponded to the optimum we could achieve in this LP relaxation. We reduced the maximum flow time problem to the unsplittable flow problem, which was shown by this construction of a graph. And we could easily translate this instance of the LP relaxation to a fractional flow by using the unique paths that showed up in our graph. We used this conjecture to turn the fractional flow into an unsplittable flow, having now those upper and lower bounds that are satisfied on all arcs, and then we got back to turning this unsplittable flow into a solution of the IP, and it turned out that this actually satisfies this approximation of 3 opt. Okay, so this kind of conjecture or the unsplittable flows in general are very interesting for the machine scheduling. So just to summarize what we have so far, because now that you know where we're going here, it might be interesting to have a look at the known results. So the upper bounds are proved in a clean manner. We have an algorithm for that. So if we want to, for a given flow, find an unsplittable flow only satisfying the upper bounds, then it's all fine. A result of Dienes, Garg, and Gumans from 1999. We have a proof of existence for unsplittable flows that satisfy the lower bounds, the arcwise lower bounds. So there exists an unsplittable flow such that y is at least xa minus dmax, and the conjecture is true for demands that are integer multiples of each other. So in this case, this is also algorithmical. So for this special case, we could already use it for the machine scheduling, but it's not this interesting. So for instances where the processing times are multiple integers of each other, we in fact have a constant factor approximation. And for the general case, we have those slightly weaker bounds here. And unfortunately, working with those factors here is somehow unmanageable for the machine scheduling application we had. So it might be possible, of course, to extend this to somehow having bounds of O of Dmax. Then we would still have a constant factor approximation for the machine scheduling, but this doesn't really help us here. It's not easier to have like constant times Dmax here for the lower upper bound. So it doesn't make things easier. We, however, conjecture that such a flow exists and can be found efficiently. And this, as you've seen, would imply a 3 approximation for the maximum flow time problem. Open problems are somehow clear. We're still working on this problem here for the lower bounds. We would like to have an algorithm finding this kind of flows. Hopefully, we're like having the right tool to also use it maybe for those low and upper bounds simultaneously. But all ideas are welcome. Yes, so that's it. Thank you for your attention.